Hi, this is Nathan Tintle. In this Learning Goal video, we'll talk about how to recognize the relationship between sample size and interval width, and we will use the Affordable Care Act dataset to talk about this learning goal. Now, in the main survey, researchers talked to 1,034 U.S. adults about their opinions on the Affordable Care Act and whether or not it's had an effect on them. An interesting subgroup of interest would be individuals who are currently without health insurance. Interestingly, the poll found that among this subgroup, folks who don't have health insurance, 70% stated the law had not affected them, which was very similar to the 69% in the overall sample. So the question is, how will this confidence interval be similar and different as compared to the original confidence interval? Well, the interval on the uninsured folks will be centered at approximately the same place because 69 and 70% are approximately the same. The big difference is going to be that the interval on the uninsured folks is going to be wider because the sample size will be smaller, because uninsured folks are only going to be a subset of the total sample of 1,034 individuals. How much wider will it be? Well, in order to answer that question, we need to know the sample size. We use the theory-based inference applet to compute confidence intervals for three different sample sizes, 100, 250, and 500. You'll notice that the sample proportion is 0.7 in all cases. And we're just trying different sample sizes to see what impact those different sample sizes have on the confidence intervals. Notice that the confidence interval for a sample size of 100 is the widest and is the narrowest for 500. Specifically, if you focus on the bottom row of the table, you'll see that in each case the sample proportion is 0.7, and the value that we're adding and subtracting, that's called the margin of error, is largest when the sample size is small, around 9% when the sample size is 100, and smallest when the sample size is large. It's around 4% margin of error when the sample size is 500. So what's the key idea? Well, as the sample size gets larger, the confidence interval gets narrow. Now, we might ask ourselves, how can we understand why that happens? Well, first, the intuitive reason. As we increase the sample size, we get a better estimate. I think our intuition says that. Bigger sample size, especially if it's a random sample, gives us a better estimate. Secondly, the standard error is less. Remember, we talked about this earlier in the course. As we increase the sample size, the null distribution has less variability. Well, the variation of the null distribution is the standard error. It's exactly the thing that we're multiplying by a multiplier and is giving us the margin of error. So as the sample size increases, the standard error decreases. And you can see this explicitly in the mathematical formulas at the bottom of the slide. For p hat, the standard error is the square root of p hat times 1 minus p hat over n. Notice that n is in the denominator, so as the sample size gets bigger, the standard error is going to get smaller, so the margin of error is going to get smaller, so that confidence interval is going to shrink. Same thing if we're computing a confidence interval on the sample mean. The standard error on the sample mean is s over the square root of n. As the sample size increases, the standard error decreases, the confidence interval shrinks. One word of caution related to standard error and confidence interval width, called the law of diminishing returns. It goes like this. Yes, as the sample size increases, the margin of error decreases, the confidence interval shrinks. But the benefit of adding additional observational units to your sample reduces. For example, the first 100 observational units get you the most reduction in standard error. If you go up to 200, so you add another chunk of 100 observational units, you get some improvement to standard error, but not as much. If you add another 100, it's some improvement, but not as much as the previous. And so what happens is, as you keep adding additional observational units, the reduction in the standard error continues to decrease. That decrease is actually proportional to 1 over the square root of n. What does this mean? It means that while additional sample size does improve the precision of your estimates, you need to be cautious because by the time you get up to, say, thousands or tens of thousands of observational units, you're not really gaining much in terms of reducing the width of your confidence interval due to the law of diminishing returns.